Hello, everyone. Welcome to this talk about DOTS scaling monobehaviors and game objects. My name is Rohan. I love playing video games. I love watching them. I love making them. I just all around completely love video games. And I work as a platform engineer at SuperGaming. I'm responsible for a lot of low-level systems that are present on the Indus platform. Uh, I consider myself to be a strong proponent for good architecture. For me, good means it's scalable, it's modular, it's performant, and I feel that a lot of these scalability, modularity, or performance issues get resolved even before you encounter them if you have good architecture. And that's enough about me. What exactly is this talk about? So, uh, this talk is primarily going to be about architecture. Within architecture, we've used game objects for a very long time now. They're reliable, they're universally adopted, they're a time-tested method of scripting gameplay. We've used them to create gameplay for years now. And we also have dots. Dots is a set of features to take better advantage of modern hardware. And to take better advantage of modern hardware, you can take advantage of multi-threading, SIMD, etc. And the architecture that we'll be talking about today is something that we internally refer to as monobehavior systems. And that is using game objects and dots in unison. So before we get into how exactly you can do that, let's take a very quick look at what dots is. So dots, the thing to note is that it's a stack, it's a set of features, and we're going to be looking at a subset of these features. Firstly, we'll start with native collections. So native collections are something that let you allocate memory without having to trigger the garbage collector. A lot of times we've had to write a lot of pools in C#, and this is something that everyone just hates doing, honestly, because it's not fun. We want to just make the game. And so what native collections do is they let you allocate a lot of native memory, and they make you responsible for deallocating them. How exactly does this work in a Unity context? So Unity provides you with a lot of reports regarding memory leaks or any kind of data races, etc. Native collections by themselves are extremely safe with regards to data races. They also have some custom allocators based on the lifetime of the allocation. So for example, if you have just a list that's used for a single function, you don't want to be paying the garbage collector costs for it. Then you have job systems, and job system is a multi-threaded task scheduler. It checks for atomic safety when you schedule a job. So by default, they give you better architecture. One way of doing multi-threading is just using OS primitives such as mutexes, semaphores, etc. And the other way is to do it in just with overall better architecture. And the safe way to access data is either you have read-only access from multiple threads, as many threads as you want, or you have read-write access from a single thread. That's in essence what a job system is. It lets you schedule these functions that will be executed when a thread is available for them. And your Burst compiler. Burst compiler provides a native compilation of C# code. It compiles C# code directly into assembly, and it also performs a lot of automatic vectorizations. And given the subset of C# that it works with, it also in general promotes better architecture. So if your code gets compiled with Burst, it by default will probably have far better performance than its .NET equivalent. And finally, the last one we'll be looking at is mathematics. SIMD is something you definitely want to take advantage of. SIMD is known to provide up to 20 times as much performance. And that is definitely something you would want in your code. But the issue is SIMD is extremely fragile. It might break without any kind of warnings to you. And within a Unity context, you can use Unity mathematics to instruct burst compiler how exactly to compile your code as SIMD. And that SIMD is not something that will just break out of nowhere. That is something you can rely on. And so now that we've looked at dots, we'll be taking a look at why exactly you would want to use MonoBehavior systems. And the thing is, we have a lot of existing APIs in Unity. We have GameObjects, mesh renderers, components, etc. And a lot of these are something that you cannot access on separate threads. You only have access to them within a main thread, and even then, only within the only as long as one of the Unity callbacks is a part of your call stack. You cannot, for example, access a transform of a game object from a separate thread, and that is by design so that you don't run into data races. And we have a lot of these existing APIs that we would like to work with. And MonoBehavior systems are a form of architecture that let you take advantage of these existing APIs while also taking advantage of dots. Then we all have a lot of existing code base in our projects. It would be a significant refactor to it would be a significant refactor because usually we have a lot of tested code that is working, code that has been months in writing. And finally, you have the team familiarity to consider. You want to be able to leverage the prior experience of the content creation team, even the rest of the engineering team, if you want to truly put your product out. That's just good production. And MonoBehavior systems are something that let you take advantage of both dots and the existing systems that you might have. They're a good pattern to follow to translate your existing knowledge with regards to how Unity works and ramp it up towards how you might be using something like entities. And that brings us to what exactly is our use case, how exactly did we come up with MonoBehavior systems? So at SuperGaming, we're making Indus Battle Royale. Indus Battle Royale is a 100+ player battle royale. And for us, scalability is a must. Our target platforms range all the way from budget smartphones all the way to very high-end PCs. And while our content needs to scale between these two ranges, so does our code, right? And because of this kind of a platform range, performance is a product requirement for us. Indus has to run on all of these systems. So dots is the obvious choice, right? But we have the same issues as everyone else. Majority of the team is familiar with MonoBehavior and GameObject workflows, and we have a considerable amount of object-oriented code base. And just as everyone else, it would be really hard to quickly adopt a new workflow across the whole team. And so for us, a hybrid approach was definitely needed. And this hybrid approach came in the form of MonoBehavior systems. It's something that we started with to take advantage of dots, and it's something that we've evolved over the course of production, and it's something that we're actually using already in production. And before we take a look at MonoBehavior systems, though, let's first look at a MonoBehavior itself, right? How exactly do we use it? So a MonoBehavior consists of configuration. This is all a serialized primitive data, for example, what the max stamina is that a player spawns with, or for an enemy manager, it's something along the lines of how many enemies to spawn for the player, etc. Then you have serialized references. Let's say a player gets hit or any character gets hit, and you want to make their mesh renderer blink to give the feeling of it being hit. So what you do is you get the reference to a mesh renderer and you just modify some properties on its material. You make it blink white or whatever else you would like. And All of these is handled using serialized object references. You have transform references, game object references, etc. And in this way, we use inspector as a way to configure our static data, as well as inject a lot of dependencies. And the MonoBehavior can also have its own internal state. For example, for a character controller, it would be something along the lines of what direction it is currently going in. That's something you want to cache in case you want to use it further in your code. Any kind of internal state that a MonoBehavior might have. And finally, you have the actual behavior. This is the core logic that runs on the data that you have provided, on the members, the fields that you have provided. And this code might be called from your other objects that call it externally, or it might also be called from one of the Unity events to start, awake, update, etc. And so what exactly is a MonoBehavior system then? A MonoBehavior system is an external object that performs calculations of several instances of objects en masse. So on enable and on disable callbacks of every instance, we register that particular instance to the system. And the system duplicates the configurations of these instances and stores them contiguously in an array. And it also gets rid of the states from each separate instance and instead also stores them contiguously in an array, in its own internal array. And this is in essence what a system is. We use an external object to run the logic, the behavior over multiple instances. And what we do exactly is we take into account the configurations and we generate the state of the object. It's an input-output type of a system. It's a data transformation. And all the logic that originally ran inside an update loop for all separate instances, we run all of it within a single update. We run all of it in batch. This lets you save a lot of L2 cache misses because all of your data is stored within a single contiguous array. And the transformations that you're performing on them can take advantage of other modern hardware features such as prefetching or even SIMD, for example, if it is relevant to your code. And based on these data transformations, we check if the state of one of the instances has changed enough. And if it has, then we pass on a callback to it and let it handle its own logic. For example, if you have a system that calculates whether or not the player is in range of an enemy, then what you'll do is you'll check for the change in that state. Was the player not in range in the previous frame, and is the player in range in the current frame, or vice versa? And based on that change in state, we pass on the callback onto the MonoBehavior instance. And after that point, that particular instance is responsible for whatever state it wants to handle. This also, again, lets you prevent a lot of memory jumping that you might be doing if you're running it per instance. And because your data transformation is extremely base level, you're just working with two separate streams of data, the configurations and these states. What you can also take advantage of is multi-threading. You can just schedule a job at the end of the tick function execution of a system, and you can synchronize it at the start of the next frame. After you synchronize it, after your data transformation is complete, then you can check whether the state has changed for MonoBehavior instance and appropriately call the on-state change callback. And this is something where job system is extremely useful. It has very, very accessible APIs to schedule a job and also to complete a job, to make sure that the job is completed before you execute any further code. And within this context, this is sort of how it would look. This is sort of how the threading overview would look. So when the tick of the system is executed, first of all, you can see in the top row on the main thread, when we synchronize the jobs, when we complete the job, after that, we execute all the object-oriented logic we had with regards to the instances, and then we schedule the job for the next frame. And these jobs, they're usually picked up by whatever worker thread might be available, whenever they might be available. And so, for example, a worker thread might execute the job at any point within the frame after it was scheduled. But by the time you call complete on a job handle, by the time you synchronize it, Unity makes sure that that particular job is completed. So it's extremely accessible and extremely safe to use in that manner. But if you remember earlier, I mentioned that the good architecture for multi-threading is either a piece of data is either a thread, either multiple threads, as many as you want, have read-only access to the data, or a singular thread has read-write access to the data. And this is something that you can see here, the next slide. So on the main thread, before the synchronization is complete, we only have read-only access to the configurations. We do not have any other access on the main thread. And whichever thread was executing the job itself, it has read-write access to the states. So you can see here, after complete is called, after the jobs are synchronized, when you're running the object-oriented logic, the main thread takes back the ownership of all of this data, and it has total read-write access of the data. And after it schedules it again only has read-only access to the configurations data, because it's being read, it's probably being read from some other thread as well when the job will be executed. And this is something where native collections come in really handy, because they throw an exception when you try to access data in an unsafe manner. And one more thing you can see here is that because for majority of the frame, the system only has read-only access to configurations array, how exactly would something like registering work, right? What happens if an instance tries to register itself to the system within this, during the time when the system only has read-only access to the configurations? It doesn't even have read access to the states. And so for that, what we use is command buffers. And so whenever, for example, an instance registers or deregisters itself, or even tries to set its own configuration. So for example, in the same, whether or not the player is in range example, when an enemy's range changes, it tries to set that particular configuration value. It tells the system that its range has changed. And so what the system does is it buffers all of these commands. And upon its tick, as in the next time it ticks, it's after it completes the job, after it takes ownership, full total read-write ownership of configurations and states, it executes all of these buffered up commands, and then it clears up the command buffer. And you can see all of the data read-write access with the green arrows. Register will be writing to the buffered commands. Deregisters will also be writing to the buffered commands. And then during the synchronization point, the system will be reading from the buffered commands to execute them, and then it will clear all of them all at once. And so this is how you can use synchronization points and command buffers to maintain atomic safety while still having good architecture. And that, in a sense, is how a MonoBehavior system would run. Instead of running a lot of code per instance, you run all of it in batch in singular system. And you take advantage of synchronization points and command buffers to make sure that all your data, that you don't face any data race issues, that all of the data stays safe. And how you exactly run the system is using another MonoBehavior that we refer to as system manager. And conveniently, the initialize or shutdown or tick functionality can be executed from on enable, update, and on disable callbacks. And you can also take advantage of something like runtime initialize on load and other Unity events to make just a global singleton so that you don't have to check very often whether or not the system is available, whether it's null, etc. And that, in a sense, is what a MonoBehavior system is. And where exactly did we use it? I mentioned before that it is something that has evolved over time. So we've used it in Indus level of detail system or LOD system. So what exactly is the Indus level of detail system? So game development is a lot of smokes and mirrors. Usually you have very limited bandwidth. You have limited CPU resources, limited memory resources, but the quality you would want for your game is endless. And so what you want to do is you want to prioritize the quality of features that the player is the most likely to notice the lack of. They would notice that the quality is missing in places. And this is something that we want to avoid. And so we used an optimization system that prioritizes the quality of features based on the player's interest, as in how big are they on the screen or how distant are they from the player, etc. And we wanted a custom LOD system that can calculate a LOD index based on just any arbitrary occupancy. If you have a matrix in the world, if anywhere in the world you have a position, rotation, and scale, you can, in essence, have that and some bounds. And this is your occupancy data, right? This is the representation of what kind of a space that this object occupies. And based on the space, we run some logic to determine how big it would be on the screen and how much resources it should be allocated. And that begs the question, why not Unity LOD groups? Well, we do use Unity LOD groups in our code. They work great for renderers. They have built-in features for example, crossfade when the LODs transition, when the renderers transition. Unfortunately, they cannot calculate a LOD indexes based on any arbitrary occupancy. They're designed for mesh renderers, and they were great in that context, but we had more use cases in mind, as we'll see a bit later. And so why data-oriented design for this, right? Why did we need data-oriented design for this particular LOD system? Well, first of all, just the sheer number of objects that we had that needed their LOD indices calculated. And because this is an optimization system, we did not want it to have a longer CPU main thread time than, let's say, the performance that it was already saving. That is counterintuitive. That would actually worsen the performance instead of improving it. So we had to use data-oriented design for this. It was a performance-sensitive system. Secondly, it was a low-level transformation. You multiply a matrix with bounds and you get another matrix. Even the camera itself can be represented as a matrix. And we just perform some matrix multiplications in order to determine how big an object will be on the screen, and some distance calculations, very basic distance calculations to determine how distant it is from the camera. And based on that, we modify the resources allocated to a given instance or a system. And we have a very clear divide in Indus between what is simulation code and what is presentation code. And this is, in a sense, a model view pattern where the view looks at the model and sort of generates itself. And for us, for a view-only system, for a presentation-only system, one-frame multi-threading latency was something that we found acceptable. Our simulation has to be completely accurate, completely precise, but a presentation can make do with a bit of compromises. And where exactly did we use this LOD system then? Well, firstly, we used it in RegLODs. So for example, for remote player characters, if they're unimportant to the current player, to the local player, we reduce the skeleton complexity. Or we also use it with particles. So unimportant particles, we either don't even spawn them or reduce the number of particles, etc. We also use it with async LOD, where we asynchronously stream in and out higher quality assets based on their importance to the player. And we also use it with AnimLOD. AnimLOD basically decreases the animation frame rate for unimportant skin mesh renderers. We also use it in EdgeLOD, where we replace a bunch of mesh renderers with a lower detail proxy. And finally, we also have a generic LOD component that is a spoilerplate for quickly prototyping whether or not LOD system can be applied to any other system, etc. And this is AnimLOD in action. We went from 17 FPS all the way to 80 plus FPS by just reducing the animation frame rate of distant objects, of distant characters. And I would also like to note that in this particular, for any kind of LODs, we do not have any kind of main thread footprint of any LOD system. All of the code is executed on a separate thread, and on the main thread, it only sets the level of detail that a particular system might be allotted based on the index. And this is something where we also leverage a lot of Unity ecosystem. For example, we had read-only inspectors that help us slice a structure of arrays into array of structures. All our configurations are stored in a contiguous arrays, and that is not very helpful for debugging. And so read-only inspectors help with that. We also have a lot of custom gizmos. Visually diagnosing systems is always much easier than always connecting a debugger. And we also use a bunch of scriptable configurations to data drive the behavior of the system itself. And we also have a bunch of code gen to generate some of the code for MonoBehavior systems. Within the MonoBehavior systems themselves, we basically encapsulate the state and the logic that runs on it. They hide their implementation details from the instances that register to them. We can also override it for some specialized behaviors. That's how we're able to use them for all of these separate systems. And we also use interfaces for the system MonoBehavior interactions. And we practice all of these pillars of object-oriented programming: encapsulation, abstraction, inheritance, and polymorphism. And what this means is that while data-oriented design is a lot of criticisms for object-oriented programming, it does not necessarily, they're not, the incompatibility there is merely perceived, that you can use both of them in unison. You can use GameObjects and DOTS in unison. And that's it for the presentation. So just some closing thoughts. Some basic stuff that I learned while implementing all of this. You always want to determine the base data transformations. Notepad algorithms help a lot with these. Object-oriented programming actually works wonders when you have less granular objects. They provide very clean interfaces. And if you have better context, you can design a better system. What is the min, max, or average of the data? How often do you need to recalculate it? Or even what is this acceptable staleness of data? How stale can your data be for you to still have good enough results? And object-oriented programming and data-oriented design are not inherently compatible. You can have good architecture with data-oriented design, and at the same time, your object-oriented code can also still be a lot more performant if you take advantage of the data-oriented design features. And thanks a lot for attending this talk. My name is Rohan. I'm a platform engineer at SuperGaming. You can reach out to me, and in all these places. And for more information regarding Indus Battle Royale, please visit indusgame.com. And I would like to especially thank the Indus and SuperGaming team for helping me through this presentation. I would really like to thank Vasundhara Kanjilal for supporting me through this whole crazy journey. Thank you, everyone.